is yours. All right. So as I do sort of every day, I'm just going to go through a quick recap of the last 2 days, and then we're going to branch into our final session. So let me skip through this. Went over that. So basically, day one, we spent learning how to set up the ESC shell container environment on everyone's personal machine. It worked to varying degrees of success, but in the end, I think we got almost everyone have their local installation of EIC shell. You were able to load the pre-built detector geometry that was in our container using that command. So source of detector epic main, then this epic.sh. Now, if you actually wanted to run a simulation with that detector geometry description, then you needed a generator input file, and we learned how to sort of browse our available input data sets using this XRT command. And then finally, we ran a simulation using that DD4F detector description with NPSIM, which is basically running Jan4 under the hood. And we streamed over our data from the location on our XRT storage server. So this was basically the first day. Does anybody have any questions or concerns, or is there anyone who didn't get that part to run within the last 2 days? I think everyone was able to run the simulation, right, in the room? Okay. So continuing on. So day 2, we spent learning how to visualize the detector geometry that we used. So one option, again, like every time you start your container environment, you'd have to load a detector geometry that you want to work with. So you do that first, and then you can do this command, dd_web_display, export the detector geometry configuration that you want. And this will produce a file named detectorgeometry.root in your current working directory. Upload this file to the geo viewer that's online, and then you can right click on the default little square over there, and then draw, and then default again, and that will pop up the detector geometry, and you can try to manipulate it or see what's in there by browsing through the tree. I think there was 1 or 2 people who had problems loading the geometry from their Linux file. I want you to try doing that. I think it has an issue with the file permissions. So try changing the permission on the detector geometry file and see if it works. So I'll come up to you, and then we can try it together and see if we can get it to work. All right. So there was another one, and this one I couldn't get it to work for any of the Mac users now. But there's the Pyrobird or Firebird event display. And this one, again, you open your container environment and you type in Pyrobird serve, configure the detector geometry that you want to use, and then you can pop up the event display. And that's another way to do visualization. I have contacted the developer and trying to figure out a way to get it working on Mac. So if I figure it out, I'll post the link on here as well. All right. And then the exercise that we were kind of going through yesterday was we worked with the pre-built detector geometry that we had in our container, but how can we do customization? So you can clone the Epic repository onto your local machine, and then you can build it. And then you have to source, again, this epic.sh that's particular to your local installation, not the one that's pre-built into our container. And then again, you can either run the simulation or do visualizations, whatever you want to do. If you want to make customizations, there are basically three folders that are most important. So there's the compact folder, which contains the XML files that has all the constants, which defines the positions and dimensions and materials of specific subdetectors. There's the configurations folder, which is just YML files that describe which sub-detectors should be turned on in the global detector geometry. So you can, if you're only working on a specific sub-detector like the top or like one of the tracking detectors, you can turn off other detectors. Because like simulations take time if you have like everything turned on. So if you're just doing iterative development on a particular detector, you can turn off other ones that you're not interested in. And then the last one was the source file, which basically contains all the .cpp templates that describe the parameterization of a specific type of detector. So this is what persists the contents of the XML files. So you can have like multiple detectors with different XML files, but they all have the same .cpp template. So it's sort of reduces the amount of source code you have to write for describing the same geometry. And we did like a small exercise where you change one of the dimension constants in a compact file and then trying to check if you see any change in the visualization. All right. So just wondering how many people were able to like successfully make a small change and rebuild their 1, 2, 3, most of the room. Okay. So if you didn't get it to work yesterday, then when I come up to you, we can try and do it together, right? Okay. So day 3. So let me just give some context here. So for most EIC or EPIC users, they don't actually have to run these simulations on their local machine when they're trying to do a physics study or a detector study, because you simply do not have the computational power or the storage to do those on your local machine. It's just impractical. So the EPIC Simulation Production Working Group, which I co-convened with Thomas Burden from Jefferson Lab, we actually run these simulations every month, and we provide large statistics outputs for different physics generators based on tagged versions of EPIC geometry and EIC Recon. I haven't introduced EIC Recon yet, but that's our tracking and instruction software. And that's done every month. So just to give you some context, I don't know if I have a laser pointer. I don't think I do. But this month, we ran simulations of about 2 million core hours. So you're not running 2 million core hours on your local machine. I don't care if you have the most latest Mac, you won't be able to do that. So that's why we need our simulation productions. Another benefit of having the centralized production is that you have sort of a uniformity across the collaboration. Like different people are not using different things. Everyone knows that it was run with this particular configuration. So you have the benefit of reproducibility. And that's very important in science. Like you should be able to reproduce your results, even if it's simulation results. And then the other one was like how much storage this was consuming. So this month we had data of about 60 terabytes. So that's 60 terabytes for 1 month. Again, you can see it would fill up very quickly if you're trying to like store all the data locally. So that's the benefit of having these central productions that put the data onto our XRD storage, and then you can again stream that data over XRD using the sort of same mechanism that we were like running our simulations. And you saw that you didn't have to locally copy that input character file to run the simulation. Okay, another thing is, again, still going through some motivations here. So we actually also run validations on this large data sets. So we have some workflows that run a range of detector and physics benchmarks. And this all runs on the EIC web server that's at Argonne National Lab. And then it produces some image artifacts, and they're all transferred from EIC web to JLab, and then that's accessible through our image browser. So what people do is that they'll write a particular analysis, and they'll save it, they'll upload it as a benchmark to our benchmark repository. And what that allows them to do is just quickly check if anything is different month to month. So you don't have to even, run your local analysis every time, like what do you usually do? You get a file, you open root, you try to open the output and then try to make plots or whatever. If you write your benchmarks, that's all automated, and then you can just look at the plots as soon as the data becomes available. So if anything goes wrong, if you're making, like some changes in your detector and you see a significant performance degradation, it's very quick to, catch that because we run these every month. So there are a couple different tools. So there's the image browser. So this is a searchable repository of these image artifacts that we produce every month. And then there's also this tool called Capybara, which allows you can run this comparison yourself if you're interested in a very specific plot that's not part of the benchmarks yet. So you have different tools that allow you to compare your results month to month based on the simulation productions. All right. So I'm not going to go through the details of the reconstruction software. What we will do today is look at a very simple example of how to analyze the contents of the reconstructed output. So basically, the first day you ran NPSIM, that gives you a simulation output that is processed through our reconstruction software. ES3Recon, that gives you the reconstructed output. So this part here is taking over from there. So we're just going to do a simple analysis. So if you would just kindly open up that link, and then we can work through it together.
You have a laser pointer. The top button is like a little bait one. Just
this one?
Yeah, like
that seems like a power one. Oh, this one.
Yeah.
Oh, this one. Okay. Right. Yeah. So you want to go to that web address. How many people here are familiar with Google Colab? Does everyone have a Google account? I'm assuming everyone has a Google account. All right, that's good. So let me just share this. So let me share my screen. Okay. So is everyone on this page here? Right? So on a separate tab, you want to open up Google Colab, the colab.research.google.com. And then you can click New Notebook. And give it your name, standing, see, installation output. Is everyone at this stage? Anyone still lagging behind? Right. Okay, so the first step here is to, I guess they have a template already. So you can just copy and paste the contents from there. So you need the first lines here. And then to run the cell, you just do that. So this is just installing all the required dependencies. And it will take 10 minutes. So while that's going on, people who didn't get I'll start with the visualization. Yeah, that's fine. So let's see. Do you already change the permissions? Try sudo /ASC shell. Should work. Now let's export it. Yeah, first. And then now just that's it. It changes the permissions, so you're running as the go means no. Oh, this loads the pre-built detector geometry. Yeah. Now we're exporting a particular detector configuration into a file. So now you want to upload this. So what you want to do first is copy this file, the detector geometry, in a location where you have permissions. So if you do ls, do a ls space unit dash and convert the lh. Yep. Okay. You enter. Yep. You see here permissions on version. It says RWR blah blah blah. Try changing that to ch font 777. Yeah, so if you switch type in ch font space 777 space detector. Yeah, enter. Now see if you can upload it. So if you go to esc, so it'll go here. Just open up a browser. esc.github.io. Sorry, esc.github.io/QOVRS. So. Oh, github.io. For example, and I'll try to open. That's nice.
The only, I went there, I went with my advisor, he drove to the restaurant. We were from there, so I shouldn't be seeing, but the restaurant and the. I just. There's more difference.
I mean, I guess
It's in the.
front,
Right.
know.
Maybe I should. Bring my. Sweet.
Yeah,
like-
good. I guess some spots,
There's one.
like over here and.
Nice.
But yeah, yes.
And then there's. So restaurant.
Here's CVS.
Oh, great.
Nail
Yeah.
salon. Manicures.
From the city.
No, just hang out.
I'll go with it.
Interesting.
That sounds fun. A bar, basically.
Yes, I guess. Why were you sick? I can't lie.
Give stress.
Actually, I'm not seeing any alcohol, so.
Something that's.
Okay.
No, there.
That's just.
Yeah.
Yeah. No, well, that's about it. Did you get the Google call up?
Yeah.
Most people's downloads going. Yes, it depends on your internet speed.
Bigger.
While that's going on, actually, since everybody has their local container environment as well, I think we can start trying it there too. So what I'll do is, where does it go? So open up your container environment /EIC shell. Let's just show again. So wherever your EIC shell folder is, just open that. You can just make a test folder called analysis. And in the analysis folder, we will just create a simple Python script. Does everyone have that yet? So let's go back here.
Be able to join the Zoom share screen. I think they just want to record it.
Let's see if I can do that. I got kicked out last time I was trying to do that. So you can share your screen too, right?
Yeah, but I don't know if we want to do that.
Oh, okay. All right. Let me try it. If you're build finished, you can raise your hands. I don't know how many you're finished, you're finished. Right. Is there anyone whose build hasn't finished? That's probably a better question to ask. You? Just you? Okay. I guess we'll wait a couple more minutes, and if it doesn't work, we'll give up.
No, it's,
Yeah.
that's what she.
Yeah.
It's going to be like that.
How can you? Sorry. Oh,
Thank you for this. They're just cute.
Oh, you don't need to install that locally because that's all inside the ESC shell container. So if you're trying to do it locally, just do /ESC shell, and you don't need to install any dependencies when you're working locally. Yeah, yeah. Just a reminder, like the ESC shell container environment has like everything pre-installed. So when you're working within the container environment, you don't actually need to install anything. When you're on Google Colab, we don't have the ESC shell container environment. That's where you have to install all the dependencies, right? You're finished? Okay, all right. I guess everybody is done. I'm just waiting on my Zoom. Just give me a second. Okay. Okay, so if you have the if your build finished, then let's move on to the next part here. And let's just get that part, this part here as well. So import upward all the way up to here. So people who like copy paste will be happy today. So this is just again setting up some plotting libraries and NumPy and awkward array, which are necessary to manipulate the data files. So has everyone gotten this part to work yet? Anybody here for whom this is not working? No? Okay. Going once, going twice, all right. So now we have like a working setup to start doing some analysis. So so let's see. Here, just gonna go all the way here. Okay, so so what's in the simulation or the reconstructed output file? So there's a event tree, which contains, you'll see if you just list the contents of it, you'll see there's many branches. But one of these branches is the MC particles branch, and it contains the truth info for all of the primary and secondary particles that we've simulated. And then you have individual branches that record the hits from different subdetector systems. So if there's a branch called vertex barrel hits, there's a branch called, I don't know, Roman path detector is, and varies. So for every single detector subsystem, there's a branch that contains the hit collections for those. So what you're going to try to do is we'll try to access the contents of one of the files and see if we can do some plotting. So let's again, following the notebook example that's here, you can just copy and paste the command from there and see if that works for you. And I know for sure that it will not work. And then we'll figure out why it didn't work. Try running it and see if it works for you.
No, it is asking for indentation error.
Indentation error, okay. So, and does anybody know how to resolve that? Yeah, go ahead.
The last four is indented on the right, should be shifted on the left, and then the condition afterwards.
Everything should be on this side, right?
No, I think. Oh, yeah.
Everything
That's
should be
indentation there. Okay, now in my code, I also had another one, which is the 4 towards the end, which is okay. So
this one here? Oh, this one here. Yeah, that's another one, yeah. So yeah,
when I
okay,
let's I missed the first slide, so it was already identical.
Yeah, let's fix the indentation errors. So you have the first one here. So this is a Python syntax thing. I'm not gonna spend time explaining that.
Listing path disallowed.
Okay, that's somebody has discovered a new error already, so we'll try to resolve that next. All right, or type 2. All right, that's another one. Anything else?
You can select all of them. Like you can select.
Running, but it is telling the path is disallowed.
Okay, can anybody tell me what, based on what you've learned, so this is gonna only make sense to the people who paid attention to the details. It's saying that the path is disallowed. Which line do you think is the problem in the code? If it's saying if it's complaining about the file path.
I mean, the F path line.
The F path line, yeah. Read the path there. Does anybody spot that? So go back to the presentation look at the file that you're accessing before and see if there's a difference between how the file paths are listed.
EIC2.
And it's on the volatile disk and that's.
Volatile
EIC
and
not
yes,
EIC.
yeah. Yep. So somebody's already found the issue. So so this should be volatile EIC. So this was we no longer have this disk in operation, but the tutorials still have that. Change it to volatile EIC and see if that works. And if that doesn't work, then we're kind of gonna be wondering what's wrong.
I didn't get the error message.
You didn't get the error message.
Yeah.
How did you get access to the work EIC? That is very interesting. Oh, I see. I know. You copy paste the entire thing? Yeah. Oh, cool. Okay, here. So, you're
Okay,
not
yeah.
printing out the error message. We'll see. Okay. It is failing, it's just not telling you
Yeah.
it's failing.
Yeah.
Okay. It's that. So, there you go. A bunch of fruits, yes.
I also changed EIC2 to EIC.
Yes. Yeah, volatile EIC, that's correct. So you have to change the file path from work EIC2 to volatile EIC. Has everybody gotten the listing to work?
Yes.
Anybody that hasn't gotten the listing to work? No? All right, all good? Okay, so let's move on to the next step. Back here. So you want to open a simulation campaign file. And we're going to choose a specific file here, for example. So again, let's just copy and paste the code. And hopefully no more indentation errors, and there is indentation errors, so you have to fix that.
Like in a new cell.
Yes, new cell. Yeah, if you just click plus code, that creates a new cell. So that you can put them in the same cell. It's just like, it's just breaking it up so that each part is sort of modularized instead of all in one place. See if that works. Anybody having trouble seeing that particular message over there? All good? All right. So what you've done here is we've opened up the events tree, and then we're just printing out how many entries there are in the tree. So it's pretty simple root type operation. Okay. So now let's try and look into the branches. So this one I don't think the notebook has it, so you'll have to try and access it from there. So here now you can see all the different branch names. So there's momentum, MC particle momentum, and then you can explore through that. Did everyone get this output here? Anybody having issues running that part of the code? Tutorial, no? So just to remind you again, the MC particles is the truth information for the primary and secondary particles that we simulated. So this is not what's getting recorded in a detector. You can try and see if you can find a detector is branch, but this is just pointing to the MC particles here. I want you to try an exercise where change the branch name to something different. So let's try vortex barrel hits. And do you see a difference in the output? Everybody see the difference? So here now you see they're saying vertex barrel hits instead of MC particles. So we're in a different branch of our root tree. Okay. So let's just stick to the tutorial and then come back to that later on again. So revert to MC particles. So the next step of the tutorial, we want to extract momentum distribution of our primary electrons. So let's just copy the Python code from here. And paste it in the notebook. What I didn't do. Okay. Did everybody get an error? Nobody got an error. Why did I get an error? I think my oh, I see. So what do you see when you I'm just gonna have to like reset my runtime, but while that's happening, I'm just gonna go around the room. Plot. Okay. I want you to try changing go back one step, change to vertex barrel hits, see if you can plot out a different distribution. And you don't have to do it in the same cell, create a new cell, and then look at a different branch and see if you can make plus from there. So that would be the exercise.
new notebook.
Oh, you don't have enough storage.
Your
You might
mom.
have to clean up your Google site a little bit. Yeah, you can use your personal Google account. Yeah. If you have a personal Google account, you can open that and then create a notebook from there. Yeah. You just have to log into that account. How are people doing with their? Yep.
Logan, you see the different names of the branches?
Oh, so you want to list all the branches?
Yeah, the
Yep.
the possibilities.
Yeah, I haven't put that on there yet. Let me just put that into the tutorials.
Okay.
Yep. Second. So for people who are interested in okay. So for people who are interested in seeing what's in the keys, The different branch names, you can just type in tree.keys. And that will show you all the branches that are available. This is, of course, after you've loaded the tree path. If you're interested to learn more about the analysis framework that we're using here, this uproot in Python, there's a very good tutorial from HSF, which is, I think, High Energy Software Foundation. I will link it in the talk after we're done here, but you can look at that if you want to learn more about uproot. So that's pretty much it. Don't have anything additional planned for today. So we just did a very simple exploration of the tree. And if you have questions about, making different plots, browsing through them, feel free to ask now. I'm gonna stop sharing here. If people have questions, I'm still here, so you can go around the room and answer your questions. You can stop recording it.